Next, we'll discuss the background from linear algebra and linear systems that we're going to use throughout this course. Some of the definitions will be for a matrix. This is an n by m two-dimensional array with the elements aij, and the first dimension is the number of rows, the second dimension is the number of columns. And the elements of A sometimes will be denoted as lowercase aij, sometimes as cap aij. A vector will be denoted as a column vector. This is the column, elements A1 through AM, column of AI, and it's really an n by 1 matrix. The transposition operation of a matrix is denoted by an apostrophe, and the transpose of our original matrix A is A prime, A transpose. Elements now are AJI, and starting from A11 to AN1, and then A1M through ANM. With this notation, we can take a column vector A and write it as the transpose of the corresponding row vector. And the row vector now is A prime, that's the row A1 through AN. A square matrix is said to be symmetric if A equals to A prime or A transpose, in which case Aij is the same as AJI, and obviously the matrix has to be square. Some of the operations are as follows: addition and multiplication of a matrix by a scalar. The matrix C is the scalar alpha times the matrix A plus the scalar beta times the matrix B. In this case, elements of C, the Cij, are alpha Aij plus beta Bij. And all these matrices, A, B, and C, obviously will have the same dimension, n by m. The product of two matrices, A and B, that's C equal AB, will have elements Cij given by the sum of Aik, Bkj, k going from 1 to m, where obviously n is the first dimension of A, m is its second dimension, and is the same as the first dimension of B. So A is n by m, B is m by p, and the result C is an n by p matrix. Important to remember that the matrix product is in general not commutative, which means BA might not be defined, or even if it is defined, BA is not going to give the same result as AB. The transpose of a product. Take the product C equal AB. Now the C prime, C transpose, is the transposition of the product AB, turns out to be the product of the transpositions, but taken in the reverse order. So C prime is B prime, A prime. As a simple illustration, if the matrix A times the vector B gives you the vector C, and now C is in B and C are both in column form, then the row C prime is B prime, A prime, which means take them, the transpose, but the product now is in the reverse order. The inner product of two n vectors, and we take them as having real components, in a Euclidean space is denoted by this notation. Inner product of A and B is A prime B. So A is a column, A prime is a row, B is a column, and this is sum of AI, BI. They must have the same dimension, and it is a scalar, obviously. Now, it turns out that in probability theory, we have a counterpart of this inner product that we are going to use for random variables, because random variables can be looked upon as vectors in a suitable space. And this would have applications, as we'll see later, in linear minimum mean square error estimation. The outer product of two vectors, A, B prime, A column, B in row form, is the matrix C with elements Cij given by Ai times Bj. Obviously, the two vectors A and B now don't have to have the same dimension. An n vector outer product with an m vector is an n by m matrix. Now, going back to a square matrix, let it have dimensions n by n, the trace of such a matrix would be the sum of its diagonal elements. So the trace of the matrix A is sum of aii, I going from 1 to n, and it is the same as the trace of the transposed version of the same matrix because the diagonal elements stay the same. Now, if A is m by n, B is n by m, then the trace of the product AB turns out to be the same as the trace of the product BA, even though the matrix AB is m by m and the matrix BA is n by n, which means these are different matrices, different dimensions, but their traces happen to be the same. As an illustration of this, if you take two n vectors, then A prime B is the inner product, is the same as the trace of the outer of itself of A prime B, because being a scalar, the trace of a scalar is the scalar itself, has a single element. But this is the same as the trace of the outer product BA prime. If you take a square matrix and consider the idea of the square root of such a matrix, it turns out it will be a non-unique matrix such that A square root of A times itself is A. But typically that's not the way it's convenient to consider a square root, but we will decompose a matrix A into the product of C and C transposed, which means that we can also write this, and this has to be verified, we'll see this later, L dl prime. The matrix A can be written as a lower triangular matrix L, has zeros above the diagonal, that C is a lower triangular, then C prime is upper triangular. Now L is a unit lower triangular, has zeros above the diagonal and units on the diagonal, and D is diagonal. So this is the C prime, there's a Cholesky factorization, and the other one is called the LDL prime factorization, since L prime, the transpose of a unit lower diagonal matrix, is a unit upper triangular matrix. We have the LDU factorization as another name for this LDL prime. Now, if we consider the inversion of a matrix, the inverse A to the minus 1 of a square matrix is such that A prime times A gives the identity matrix, which has ones on the diagonal and zeros elsewhere, so it can be also written as a diagonal of ones. This is the identity matrix, and obviously this has to be of the same dimension n by n as the original matrix A. the expression for the inverse, a to the minus 1, is 1 over the determinant of A times the transpose of a matrix C. C is the adjugate of A. Really is the matrix, each element of it consists of the cofactors of A. And the cofactor ij of a matrix A is the determinant of that matrix A without row I and column j, and with the proper sign multiplying it, which is minus 1 to the power I plus j. Now, there is a connection between the inverse of a square matrix and the concept of linear independence. The inverse of a square matrix exists if and only if its columns, ai, there are n such columns, each being an n-dimensional vector, if all these vectors are linearly independent. Which means if I want to have a linear combination of these vectors, ai, with some coefficients alpha I, this whole linear combination to be equal to the 0 vector, this can happen if and only if all the alpha i's are 0, which means there is no linear combination with non-trivial coefficients alpha, this is a trivial case, that can be made 0. They are linearly independent. It turns out that this also is equivalent to the fact that the determinant of that matrix is non-zero. We also use for an invertible matrix the term non-singular. So these are equivalent concepts. The determinant of a matrix which has dimension n by n, if we multiply it by a scalar, it turns out is alpha to the power n times the determinant of the original matrix, because a scalar will effectively multiply each element you pull out from each row or each column an alpha, and that's why you get alpha to the power n. It turns out this will be convenient in writing the probability density function of a Gaussian random vector. Is another result that will be very useful. If we have a matrix which is n by n and we partition it, P11 is an n1 by n1 block, P22 is an n2 by n2 block with n1 plus n2 equal to n. Then we have P12 is n1 by n2, P21 is n2 by n1. Now, we invert this whole matrix and relate the blocks, the counterpart blocks of the inverse to the original blocks. So again, V11 is n1 by n1, V22 is n2 by n2, and so on. There is a convenient relationship that we'll use later in simplifying certain estimation equations. And this says that V11 is given by this particular combination, this expression in terms of the blocks of the P matrix, and there are two different forms which are algebraically equivalent. There are similar expressions for V12, V21, and V22. So, nobody has to remember this. That's why we have them referenced for convenience in the book. Okay, now there's a matrix inversion lemma. It turns out that an expression consisting of the inverse of a matrix P plus an H transpose inverse of matrix R H can be written in terms of P and R as P minus PH transpose HPH transpose plus R inverse HP. The matrix P is n by n, H is m by n, so remember now H transpose is n by m, R is m by m, so obviously this product, once carried out, is an n by n matrix, so it's compatible. Again, this is another expression that will allow us to have simplified versions. And as a matter of fact, you can find that the two equivalent expressions for the inversion of a block matrix partitioned into blocks, for the V11, these two expressions are effectively already using what is called the matrix inversion lemma in providing those two different forms, which are algebraically equivalent. The derivation of this is easiest to be done by just verifying it. Take that, multiply it by itself, and see that, take the two forms, and you can see that the expression on the left-hand side in parentheses multiplied with the expression on the right-hand side should give you the identity matrix. There's an alternative form of this matrix inversion lemma given here, and again, the verification is quite straightforward. Now, these have direct application in the derivation of the recursive form of the least squares estimation of parameters, as well as in linear estimation for dynamic systems. It turns out they yield us various forms of the Kalman filter, and I should also point out that the least squares estimation of parameters and state estimation for dynamic systems, the Kalman filter, have a lot in common. They can be put into very similar forms. They're not exactly the same thing, but quite similar. Now, when we are going to discuss estimation, it turns out there is a convenient concept of orthogonal projection of vectors. Before this, we go back to the inner product of a vector with itself. That's inner product of A with A. Remember, this is in a Cartesian form, A prime times A, which is the sum of its components squared. So A norm squared is the notation. An inner product, in its definition of a vector with itself, is required to provide what's called a valid norm. This is the so-called L2 norm. Obviously, it is squared. Physically, this L2 norm is the magnitude of the vector or its length, which can be easily seen with our definition of a vector in a Cartesian space. The so-called Schwarz inequality states that there is a relationship between the magnitude of the inner product of two vectors and their norms. The magnitude of the inner product of A and B is less or equal to the product of the magnitudes or norms of these two vectors. And the easiest way to see this, take in 2D the plane, the inner product of two vectors is the length times the cosine of the angle between them, and this gives a clear indication that the cosine being between +1 and -1, we have this inequality. Orthogonality of vectors is as follows. We say that A is orthogonal on B if the inner product between A and B is 0. The orthogonal projection of vector A on B is projection on B of A is the inner product between A and B divided by the norm square, the square of the norm of B times B. If you look at it as AB being the length times the cosine of the angle, you have one length of B here, the square of the length here, and one more time length here. So if you divide by this, you will get a vector along this B where the magnitude of B has been cancelled out, and its magnitude is A times the cosine of the angle between the two vectors. Now, it turns out that the reason we call this orthogonal projection is the following. The difference between a vector A and its orthogonal projection on B is orthogonal on B, and that's the reason for the definition. So A minus the projection on B of A is orthogonal on B, and we have a nice illustration here. This is the vector B, this is the vector A. This is the projection of A on B. It's along B, and it is the magnitude of A times the cosine of the angle between them. So that's the definition. Now, if we look at this, what is the difference between A and its projection on B? You see it here, and clearly this is an orthogonal projection, which means this angle is 90, which means this difference is perpendicular in the plane on B, or in general it is orthogonal with our general definition of vectors. A number of other concepts will be needed, namely the gradient is the first one. The gradient operator with respect to an n vector x is defined as a column vector. You see, this is put in row form, but there is a transposition. This is an operator. Each component of it is a partial derivative with respect to one of the elements of the vector x. So, if I take del x, and this is now column vector, d to dx1, all the way down d to dxn, and multiply it with the transposed of a vector f. What do we get? Remember, this is a column vector. You have to multiply it with a row vector to get something meaningful. That's why the need for transposition. You get df1 to dx1 here, to dfm to dx1, and so on. So this is the gradient of an m-dimensional function f. It's a vector with respect to the n-dimensional vector x. Now, the Jacobian matrix turns out to be the transpose of the previous expression. It is written in a very compact manner as f sub x of x, where the sub x means derivative, the argument is x. At another very compact and not very rigorous way of writing, partial of f with respect to x, but remember, f is a column vector, x is a column vector. So this is to be interpreted as a purely symbolic notation. The exact algebraic expression is given by del x column, fx transpose row, and the whole thing transpose. And now you get df1 to dx1 through df1 to dxn. Element 1, 1, element 1n, element m1, element mn. In most cases, the dimensions of x and f will be equal, in which case we get a square matrix, the Jacobian, but it's not necessary. Now, it's easy to see that del x of x prime gives the identity matrix. These are some of the simple exercises. It is always suggested that you go over such algebraic derivations to ascertain that everything is okay. So del x transpose is the diagonal matrix with ones. Now, if A is a symmetric matrix, the gradient of x transpose AX is 2AX. And the way to see this, you take the gradient with respect to the first one, that gives identity, AX. Then you switch between this and this. Now, the second becomes the first. That's the second time you have to take the derivative for the second location. But you put it in the first, because remember, this is a scalar. And if it is a scalar, you can transpose it. So you get the second time an AX. That's why the result is 2AX. Some more expressions that we need are the definitions of eigenvalues and eigenvectors and connection with quadratic forms. The eigenvalues of a square matrix are scalars lambda I such that A times some vector ui is that scalar lambda I ui. The vectors ui are called eigenvectors or proper vectors or proper directions, and what a multiplication by a matrix does to this vector is you get back the same vector scaled. So that's why it is called also proper direction for that particular matrix. Now, if the eigenvalues are distinct, you are guaranteed to have n eigenvectors. Otherwise, the number of linearly independent eigenvectors might be less than n. It turns out that there are ways of expressing this. You are not necessarily guaranteed that all the eigenvalues are distinct, for a matrix can have multiple eigenvalues. Now, a matrix is non-singular if and only if all its eigenvalues are non-zero. And this follows from the fact that the determinant of a matrix turns out to be equal to the product of its eigenvalues. The rank of a matrix, and now we'll take a matrix which is not necessarily square, equals the number of its linearly independent rows or columns. If we're talking about a square matrix, it turns out this is the same as the number of its non-zero eigenvalues. A non-singular matrix, obviously, you need a determinant to be non-zero, must be full rank. In that case, you have a full rank n by n matrix. Its columns and rows span the n-dimensional space. No column is a linear combination of any other columns. That is the essence of guaranteeing invertibility. Quadratic forms, if we have a vector x, say of dimension n, matrix A, n by n, this x prime ax is a scalar. It's called a quadratic form. It turns out that the matrix A can be considered symmetric because every matrix can be decomposed into its symmetric and skew-symmetric components, a sum of two matrices, and the skew-symmetric has zero diagonals. Aij is minus Aj, so ends up with contributing 0 to the quadratic form. Therefore, you might as well take a symmetric matrix here. A positive, definite, or semi-definite quadratic form is one which is positive or non-negative for all non-zero vectors x. And we write the quadratic form, if the quadratic form x prime ax is for a given matrix A positive for absolutely all x's that are not the zero vector, then we say the matrix A is positive definite. If this quadratic form is non-negative, which means greater or equal to 0 for all non-zero vectors x, then A is positive semi-definite. Clearly, if x is 0, this will be 0, so the point is you end up with squares of the elements of the vector x, and this is why it's going to be positive. No matter what the vector x is, can have negative elements. As long as they are non-zero, you can get, if A is what is called positive definite, you're always going to get a positive quantity here. Now, if the matrix A is positive definite, what we have, the x prime AX in the previous equation, is the squared norm with respect to the matrix A of the vector x. And this is one of the notations. Actually, this notation was used in the original Kalman filter paper by Kalman. X norm squared with respect to A. So this is the x prime AX. Remember, if A is the identity matrix, you just get the standard squared norm x prime x, which is the sum of its components squared. Now, a matrix is positive, definite, or semi-definite if and only if all its eigenvalues are positive or non-negative. So really the connection between positive definiteness and eigenvalues is quite straightforward. Now, when we talk about comparison of two matrices, an inequality can be written as follows. The matrix A is, say, smaller than the matrix B if and only if the difference B minus A is positive definite. So, if B larger than A means B minus A positive definite, or if it is positive semi-definite means it is not larger. The same, A is the same or smaller. So this is how we define inequalities between matrices. We can take the outer product of a vector with itself, A prime, A transpose, which is called a dyad. If this is a positive semi-definite matrix, it turns out it has rank 1, has a single eigenvalue, which will be the norm of the vector A. Its only eigenvector is A. It has a rank 1 and all its other eigenvalues are 0. Now, the sum of dyads of n vectors, A sub I, each is an n vector, with positive weights alpha I. So sum of alpha I, AI transpose, this is a dyad multiplied by positive scalars. That's A tilde. That's a matrix. Is at least positive semi-definite. So what you end up with here is sum up a bunch of positive semi-definite matrices, and if these m vectors we have span the n-dimensional space, obviously you need at least n such vectors or more, then our expression A tilde is positive definite. So if you have enough vectors to span the space and all these scalars alpha I are positive, the resulting matrix is positive definite. And this is very important later we'll see for observability in parameter estimation, because it turns out that for certain problems, to guarantee observability, you've got to do something. We'll see the details later. And it does boil down to the requirement that you have enough such vectors that the result A tilde matrix is positive definite, because we need to invert it. So the invertibility of a certain matrix that is called, turns out, the information matrix, is a key in guaranteeing our ability to estimate certain parameters.